Hello, hello, hello. Good afternoon, Internet. Welcome. Welcome to yet another NL Mathman Math Help stream. And this is day 27. It's a good number. 27, it's a great one, right? It's a nice cubic number, right? 3 cubed. That's right. Don't be a square. Don't be a square, right? Because squares are flat. They're two-dimensional, right? I mean, at least it's better to be a square than it is to be a line. That's for sure. Like, in Pulp Fiction, when Uma Thurman said not to be a square and did that sort of thing, right? I mean, you know, it has two dimensions, right? It's got length and width. Well, that was the scene where like it actually followed. You remember that? People, you've seen Pulp Fiction, right? You've seen Pulp Fiction, haven't you? Yes, boy. Where she does that, and then like it follows, like there's a little like undiegetic, I guess, just sort of like a meta like effect that follows her hands there. It's the only one in the whole movie. It's just so weird, right? It's like clearly it's not meant to be part of the scene, right? We're not John Travolta's character is not there assuming that Vincent Vega, I know what his character's name is. Come on now. Is not assuming that Mrs. Mia Wallace has some sort of like magical power where she can like draw a dotted square in midair just with her fingertips, right? Like so clearly that was put in by QT by Quentin for us nerds to revel in the I guess the idiosyncrasy of his anti-diegetic filmmaking. Well, diegetic is usually used more in games, I guess. No, I guess it would make sense in a movie too. Anyway, I'm just here rambling now. As usual, right? This is what happens. This is what happens, Larry. This is what happens. This is what happens. When you find a stranger in the Alps. This is what happens, Larry. Um, I'm nailing the movie references today. Look at that. Look at me go. Um, over here to the side, right? Got another nice picture of myself. This is from that same hiking trail that I've shown a few pictures of before. This is from the Green Gardens Trail. As you see, the light is starting to set there. This was near the evening. We were just coming out of the woods after a bit of a descent down toward the coast. We were coming up to the rest sites. Right, you can see me kitted out with my bedroll, the tent wrapped up there, bedroll down at the bottom. Got bottles of water on either side. I had one on both sides that I tried to take from evenly, right, to keep it balanced. You got to keep it balanced. I got my cell phone there stuck in a sort of a chest pocket. Yeah, it was good. And you notice I got the waist and the chest strapped up on the backpack. It's proper. Yep, it's important to have proper ergonomics. But yeah, it's another little look at maybe the things I'll be able to get up to this summer. Hopefully I would really like to get back out at the hiking. That'd be a great time. Um, got one other thing to talk about. I really wanted to show this on stream today, just because I haven't indulged myself in showing off my cooking in a little while, right? And I figure in my first like, you know, 5 or 6 minutes of being live, this is the time to do it, right? So I've got something. I do want to show off this. This is a this is the last that's left of it, but this was quite the culinary creation. Although not really a creation, it's um, pretty basic innovation, I suppose. But if we look over here, right, we can see it. We can see it here in the background a bit better. Look at that. What is that? That that is cod au gratin casserole is what that is. Let me shrink myself. Let me make myself a little bit smaller here on this one. There we go. Now you can see it a bit better. Look at that. Look how amazing that is. This was I did a layer of paracooked potatoes down bottom. You can see if I get in there. Get in there. You see the potatoes down below? Yeah, there it is. Got a layer of paracooked potatoes, paracooked carrots and broccoli. Put in some fish, some fresh cod that I paracooked and put in there. Poured a very nice homemade bechamel over the lot of it. And then some breadcrumbs on the top. Made it a homemade bread with some Mount Silo savory in there. Toasted it up right nice. Boy, oh boy. I gotta say, mm, y'all are gonna have to just put up with some eating noises on stream today. Mm, boy, I like bechamel sauce. That's so good. I years ago I tried to start like learning to cook because once I moved out, I remember the first dish I made for myself when I moved out from my parents' place was an attempt at just chicken legs with cream of mushroom soup, and all I did was like put the chicken legs in a pan, crack open a can of cream of mushroom soup, and pour that mother in there, and it was disgusting. It was so like gelled fat over the top of it because it was like dark meat chicken and then just like concentrated cream of mushroom soup. It was horrible. One of the worst things I've ever eaten. Since that point, I set out to learn how to make like proper sauces and things like that. And gotta say, my mother's sauces like bechamel and sauce tomate, velouté. Oh, velouté is easy, right? Velouté is just gravy. But my sauce tomate and my bechamel are they're pretty nice, I must say. So I do like using those in cooking whenever I have a chance. Anyway, I'm done being self-indulgent for a little bit. You see up above me here, my topics for today. I'm going to cover inductive versus deductive reasoning. That's a topic that a student wanted me to go over today. Now, I do have these out of order here. I'm actually going to cover converting between metric and imperial units and then measuring with fractions of inches. I'm going to do that first because that's a relatively short topic, and I did have a request to go over that today as well. Um, yeah, so I'm going to briefly go over those. Then I'm going to tuck in and do some inductive versus deductive reasoning for a bit. To sort of explain that topic because it is a fair bit different than some of the other math that you will see. Now, Betty Ann, one saving grace about that topic is once you're done with it in this course, you're not going to see it much more after that. But I will still try to do it justice here because it is a fair bit different than the stuff that you've been seeing so far. But first, like I said, I am going to do a little bit on converting between metric and imperial units, and then sort of how the heck you read a ruler gradiated in inches. Right, here we go. So the first question I'm going to do is number 5 over on this page over here. So let me just zoom in a touch. Okay, zoom out a touch. There we go. On their summer vacation, the Porter family drove to Florida. It's not something you can do right now, but you know, maybe later on, maybe summer 2021. We'll see about that one. Perhaps that's wishful thinking too. We'll see. We're taking it a week at a time in this world now. But it had the following fill-ups at gas stations: 15 gallon, 16, 15, blah blah blah. What's the total amount of gas? Well, I mean that's not hard, is it? 1102A, and this is unit 1. Oh, I'm off the top a little. There we go. Excuse me. Question 5. So, on their summer vacation, the Porter family drove to Florida. They had the following fill-ups. It's the total amount of gas. So it's just going to be, obviously, it's just going to be adding these guys together. 15 plus 16 plus 15 plus 13 plus 18. Well, it's 30. It's 46. 59. 77. Not a super tough question for that part, no, is it? Part B, convert the total amount of gas to liters. Well, how are we going to go about converting it to liters? Well, we know that there's 2 different ways, and I do like to show the 2 ways to do it because one is with cross multiplying, although they're not really different ways. They're actually like exactly the same. But let me see. Here we go. This is the formula sheet that you have for this unit. So this is the one that you're going to be using. Renetta, I believe this was a question for the assignment that you did. So we have defined on here which conversion factor we can use. Now we need one that has gallons in it and has liters in it, right? So we can look over and we see, hey, this one here works. This is 1 gallon per every 3.785 liters. Now, one way that we can do this is we can do a cross multiply method, right? So we can set up our conversion factor first. So that's 1 gallon per every 3.785 liters. And that equals 77 gallons per some unknown number of liters. Right? And it's important, the important part here is that we have on either side of the equal sign, we have the same unit on top, gallon, gallon, same unit on bottom, liters, liters. Now we can cross multiply. right? If we cross multiply, we get x times 1 on the left, because this comes up here, and on the right we get 77 times 3.785. And once we multiply it together, we'll have the answer that we're looking for. $291.45. Okay. Another way that I like to do these that to me makes a lot of sense is to multiply them out but cancel the unit that you want to get rid of, right? Because the thing over here is we are trying to get this one to have liters left over. So we know we have 77 gallons to start, right? And we know that if we have gallons on top here, excuse me, we're going to need gallons on bottom if we multiply in order for them to cancel, right? So now the difference, what I'm doing here is that there's no equal sign in between these. These are on the same side. But we have this conversion factor over here, and we know liters needs to be on top. Liters per 1 gallon. We know liters has to be on top because we have to have gallons on bottom, right? This is our conversion factor. Here, and this was the conversion factor over here on that side. Right? So now we can just go ahead and multiply these two. The gallons here cancel with gallons here, and we're left with 77 times 3.875, which is still going to be 291.45 liters. Okay? So either way we go about doing that, we're going to end up with the same number of liters left, right? As long as we use our correct conversion factor, which is this guy, and as long as we then set it up so that what we're left with is a number of liters in the end, right? So now let's look at this last one. If the price of gas in Canada is that much money, actually I can zoom in a bit. Why did that zoom back out then, huh? I can zoom in quite a bit more here. The price of gas in Canada was $1.32 per liter. It was only a few months ago, huh? Boy, that was a quick change, wasn't it? How much would it have cost them in Canadian dollars for the trip to Florida? Well, of course, right? We know it costs $1.32 per liter. So if we've got 291 liters, we're going to have to multiply to find out how much, right? Because we know we're going to be spending more money. But we can still think about it in terms of the way that I set this question up over here. Because what we have is 291.45 liters multiplied by 1.32 dollars per liter. Now I know we normally put dollars in front, but for the sake of the math, I'm going to show it with the units left afterwards like we normally do. We go ahead and multiply these. Liters are going to cancel with liters. We're going to get 291.45 times $1.32. We're going to be left with 384.71. $384.71. There you go. Right? Okay. I'm going to do one more from this assignment. Then, Renetta, I'll go over the ones that you asked for the next unit specifically. And then I'll tuck into a bit on inductive versus deductive reasoning. Switch to blue so we can see that I changed question. Question 6. Derek paid $672 before tax for 16 square meters of carpeting for his living room. Later, he decides to put 12 square meters of the same carpeting in his dining room. Price of the carpeting has increased by $1.20 per square meter. Okay. What was the original unit price of the carpet? Okay. So a unit price is, of course, the price per unit, right? Now, Renetta, you did definitely understood how to do those ones, right? So the cost is going to be $672 per 16 meters squared. So we're going to divide here. 672 over 16 is going to give us 42 bucks. $42 per square meter, right? And that's literally how we read this unit, dollars per square meter, right? This is just a way of writing out that phrase in math language. So hopefully that that makes a bit of sense as to why we're arranging the numbers as we are, right? We have the number of dollars divided by the number of square meters to get dollars per square meter, right? So what is the new unit price of the carpeting? Well, all we got to do is add there, right? Because it said it went up by $1.20. So it's going to be 42 plus 120 equals 43.20. It's not hard. And for question C, what is the percent increase in price? Now here, this is an example of something that I'll end up saying to you, a good 3 dozen times during your math program. And that is one of the core issues with using books like this in distance teaching, or in self-guided teaching rather, is it kind of assumes that your teacher is there to sort of put out little holes in knowledge, or plug little holes in knowledge, put out little fires, I was going to say, but I didn't want to be that extreme. Plug little holes in knowledge that you might have, right? And how to find one number as a percent of another, well, it's not explicitly taught by this unit in this course. It's just something that they assume that you already know how to do, and if not, your teacher's there to point it out, right? But all we have to do to find one number as a percent of another is just divide, right? We divide, then we times 100 afterwards, right? So here, what is the percent increase in price? Well, we have to find what $1.20 is as a percent of the original price, right? Because that's how we determine what percent it went up by, is what percent of the original it was. So it's going to be $1.20 divided by 42. So 1.2 divided by 42, going to give us 0.02 whatever, times it by 100 because we want our percent. So we see it's about 2.9%. So roughly about 3% increase in price. How much will it cost before tax to carpet the dining room? Well, it's not hard now, is it? Right? Because we're told that his dining room is 12 square meters, but now the cost is increased. So we have a cost of 43.20 per meter squared. We're going to multiply that by an amount of 12 meters squared, right? So just to carry on doing the units like I did up here, just to show you how it works when units cancel. The meter squared on top and the meter squared on bottom are going to get eliminated. So all we're going to have is 43.20 times 12. That's pretty straightforward, right? I mean, that just logically makes sense, obviously, right? If it costs him 43.20 for 1 meter squared and he needs 12 of them, well, I mean, yeah, obviously we multiply. There we go. 518. So like I'm saying, you don't necessarily need to think of sort of straightforward math like this in these terms, but I did want to write it out like this so you see how the algebra language is consistent with sort of the concepts that you know to be true about the way we would do this stuff, right? Um, yeah, so that was what I wanted to go over for that first activity. Um, Renetta, you asked specifically about measuring um, measuring amounts with rulers that are sort of gradiated in inches. Now, it's not something that we always see here in Canada, but a lot of measuring tapes. Oh, no, that's a page for the wrong course. Hold the phone. Hold the phone. Oh, yeah, I just got to scroll down, don't I? Huh. There we go. There we are. So in Canada, we tend to see more often things that are gradiated in millimeters and centimeters, like it is here below. But pretty commonly, when you break out a measuring tape or something like that, you'll see inches on one side, centimeters on the other, just like this one, right? Um, so you ask basically how in the world is this 8 and 8/16? Well, it's because if you notice all these little notches here on the ruler, right? You'll notice each notch is a different sort of size, right? A different height. We've got this notch here is the biggest one. Well, we've got these ones that are the biggest, which are marked with a whole number. So this is a full number of inch here, right? Then you've got this bigger one in the middle. So this is half an inch, right? We call a half inch, we'd call that 1/2. Quarter inch is, of course, going to be 1 over 4. And quarters are these ones. You'll notice how it gets slightly smaller. The biggest one here is a half. This one here is a quarter inch. These ones here that get a little bit smaller than that are going to be an eighth of an inch. EIGHT8. Can't remember how to spell eighth. It's a weird word, eighth. God. You'd think this just never mind the fact that my graduate degrees in English or anything like that. Don't let that concern you. You know, who cares about reality? 16th inch, 1 over 16. Right? Now, one saving grace of the imperial system is that it does teach people, it forces people to become pretty acquainted with how fractions work, right? Which is one thing the metric system doesn't do. Now, granted, that's a small benefit. I much prefer the notion that, you know, people measuring things for sciences and engineering can just use factors of 10 instead of factors of like 17, 60, and other such nonsense. But imperial is a good example, especially inches, of how we do fraction math, right? So a half inch is 1 over 2. We know that, right? We know that half is 1 over 2. But a half is also the same as 2 quarters, isn't it? Because look here, right? We go 1/4 an inch to get there. A 2/4 an inch gets here over to this half inch. So a half is the same as 2 quarters, right? Or 2 over 4. We can see the same sort of thing down here, right? That a quarter inch, like this bit, is the same as, see, this one here is an eighth, and this is another eighth. So 1 over 4 is going to be the same as 2 over 8. 1 over 8 is the same as 2 over 16. A 16th is the same as 2 over 32, but we're not going to bother with that, right? Because generally we don't see 30 seconds of an inch represented. So a half inch is 2/4 of an inch. A half inch is also, we see 1, 2, 3, 4, 4/8 of an inch, right? So here's all these in eighths. We got an eighth, 2/8, 4/8, right? 1/16, 2/16. Well, 2 over 8 is going to be the same as 4 over 16, isn't it? Right? And 4 over 8 is going to be the same as 8 over 16. So all this is, Renetta, this is just equivalent fractions, right? You saw this before in one of the prerequisites, 2013, I think, maybe. Can't remember exactly which one. But, it's relatively straightforward when you start to see it in these terms, right? That a half inch is, of course, the same as 2/4 of an inch because we multiply the top and the bottom by 2. And the fraction stays the same as long as we multiply the top and the bottom by the same thing. Same over here, 4/8, that's the same as 8/16. Quarter inch is the same as 4 over 16. Eighth of an inch is 2/16 over 1/16 of an inch is the smallest gradation on there, right? So just to bounce over and to answer, because that was a question in your notes, that's why it's 8 and 8/16 over here, right? Because it's 8.5, yes. It's 8.5 like we see over here, but a half inch is the same as 8/16. So we could say 8 1 over 2 inches is the same as 8 and 8 over 16 inches, right? Because 8 over 16 is the same as 1 over 2. Saying instead that we went over and looked at the review sheet. This is the review sheet for the Unit 2. By the way, of course, you've finished Unit 1 just this morning. I'll send you the review sheet for Unit 1 after I'm done here today and after I send you these notes. So then you can complete that review sheet, like I said, as an extra assignment for a few bonus marks, and then carry on and do the test for Unit 1. But this is, say, the review sheet number 10. Okay, do this in a different color. So give the distance marked on the measuring tape by the arrow. Give answers to the nearest 16th of an inch. Well, we can see that that's this is the middle sort of marking, right? Or the second smallest. So we know that the second smallest marking are eighths. So that is 1/8, 2/8, 3/8. So we can see that that's one is 7 and 3 out of 8. But it's asking to the nearest 16th of an inch. Now I would be content with you saying 7 and 3/8 of an inch. But if you wanted to put that in 16ths, we're just going to times this top by 2 and times this bottom by 2. So that's going to be the same as 7 and 6 over 16 inches. Right? So that's all you've got to do for those. Okay, I hope that that answered your question reasonably well. Stream's not starting soon, stream's going. So that's a decent little overview of those questions. I am now going to move on, and we're going to talk about inductive versus deductive reasoning for a bit. Okay. Now, inductive versus deductive reasoning, like I said, is a relatively um, it's a fair bit different than some of the other topics that you have seen so far, but it's actually quite a lot simpler than it might first appear. It's just sometimes it seems a bit strange what the questions are asking you, but yeah, I mean that's just what they're asking you, right? Sometimes it is strange. But if we pop over here, this is from page 13 in the book. So this is going to be Math 2101A. This is going to be page 13. So I'm just going to show what um, inductive reasoning is through some examples. But as a definition, inductive reasoning well, that's one way of saying it, right? But inductive reasoning uses patterns to infer conclusions about future trials. So, or about, about extending it kind of. But the important part is that it uses patterns, right? So inductive reasoning, sort of, we gather the information already, and then based on the information that we have, we draw a conclusion about what might happen. Or we call these conjectures. I'll call this conjectures. Right? And by future trials, I'm just trying to phrase it very generally, just saying that if we use a pattern to make a conjecture about something, we're then saying every time in the future that we do something similar, we should get the same sort of result. The result should be keeping with our conjecture, right? So, for example, take number 7 here on page 13, right? This is a decent question. Sonia noticed a pattern when dividing square. Oh, sorry. No, I wanted to do I didn't want to do number 7. I wanted to do number 6. Never mind. So use the evidence given in the chart to make a conjecture. Provide more evidence to support your conjecture. One reason I wanted to do number 6 here is because this is one that we saw in a previous course. Actually, no, where you're doing the academic, I'm not sure if you've covered that one explicitly yet. But it is something that's done in other courses. So any other student who is watching will have seen little bits of stuff like this in other things. But we do know that a quadrilateral is basically made out of 2 triangles, right? Like look at the picture up here. Any 4-sided figure can be sort of conceptualized as 2 triangles that are put together. And then a pentagon or any sort of 5-sided figure can be conceptualized as 3 triangles, a hexagon is 4, and so on, right? Because basically every time you're adding another side, you're adding another triangle. And of course, a 3-sided figure, a triangle, is 1. It's 1 triangle, right? So use the evidence given in the chart below to make a conjecture. Provide more evidence to support your conjecture. Well, there's a very important rule that derives from what we're doing here, and that is how we find the interior angles of a shape. But a conjecture that I can draw about this is the fewest number of triangles in a shape is the number of sides subtract 2. Right? So this is my conjecture. just to show you what it is, it's a conjecture based on the data shown in the table, right? This is a good example because this one's pretty clearly fairly math oriented, right? That the fewest number of triangles in a shape is the number of sides minus 2. And well, it says here provide more evidence to support your conjecture. Well, then hexagon is there, so let's go on and do a I don't know, I don't really want to draw out a septagon here, but let me try it. Oh, if I had a oh, I do. I do. Hold on. Hold the phone, Twitch chat. Ah, I knew this was going to come in handy. Don't mind me. Here we go. Here we go. Yes. Good stuff. All right. Hold on there, Twitch Chatterino. I'm gonna find something here. I know I got one. I definitely have one, don't I? I definitely do. Let me show you what I'm doing. This is a small little coin collection. Look how rad this is. This is really good. This is good stuff. See that? See that coin there? Ancient Rome. Emperor Constantine. I paid 15 bucks for that. That's a great. I hope that's actually from there, and I'm not just being duped by some random ass piece of metal. But I have a 50p in here somewhere. I must have a 50p coin in here someplace. Sorry about all the random rattling noises on stream. Hey, do I not have a 50p in here? That's too bad. The British 50 pence coin is a septagon, right, or a seven-sided figure. So I was just going to grab it and trace it. I don't actually think I have. Didn't keep a 50p. That's too bad. Oh, there's a 10. There's a cool £2 coin with Charles Dickens on there. There's the basic £2. No, I didn't. I don't think I kept a 50p. That's too bad. That would have been useful. All right, well, I'll clean that up later. Oh, hi, how's it going, Slayer Darth? Yeah, welcome back. Brush up on your geometry. This trigonometry to brush up on before calculus. Trig is great. That's a good topic. You never get away from trig. Even when you think you are, you're not, right? Because then you start doing like sine waves and stuff like that. It's, and then all of a sudden it's like, hey, this like wave representation that is super useful in like physics and engineering courses actually derives from triangles, strangely enough, right? So you're never really done with trig. Trig is a great topic for sure. I'm just going to try to draw a seven-sided figure here as best I can. Not going to be a regular one by any stretch of the imagination. It's too bad. If I had a 50p coin here, like I said, I could have gone ahead and drawn a traced out a very even one, but these things happen. But as you see now, I'm just going to pick one vertex here, join it up like so, and we see that a seven-sided figure equals 5 triangles, right? So this is a little bit of evidence to support what we're saying here, okay? But this one is a good example to use for another reason, because it allows us to go on to sort of showing what deductive reasoning is, right? There's a formula that you can use that just determines sort of however many it is. Why did one angle decide to ask out another angle? Because it was a cute angle. Yeah, that's good. I like that. Math and puns. That's excellent. Right. So yeah, the difference between inductive and deductive reasoning is that inductive sort of proves something by showing examples that we've had already. Deductive reasoning uses what we call proofs in algebra to show that something will always be true. Yeah, n minus 2 times 180. That's right. That's right, yes. Yeah, so the interior angles of a quadrilateral is going to be n minus 2 times 180, right? Because we know that n minus 2 is the number of triangles that are in a shape, right? Where n is the number of sides, right? Or if we wanted to find the measure of each interior angle in a regular shape, we would then divide that by n. But that's an aside, because that is something that you do see in different courses other than this one, right? Let me see here. Let me show an example of one to show. Okay, this is on the deductive reasoning here now. The thing about inductive reasoning is sometimes inductive reasoning is it's a bit strange to see it in a math course, for example, right? Like, look at question 4 over here. Make a conjecture about the meaning of the symbols and colors in the uh, Francois? Francois, I think that's pronounced. Yeah, Francois flag to the left. Consider French Canadian history and the province of Saskatchewan. You'll notice that has nothing to do with math at all, does it? Like, this is a history slash geography question, right? Like, if I had to guess, I would say that, well, this is the fleur de lis. I know that the fleur de lis is a important French symbol. I honestly don't know why yellow, green, and red. Maybe the colors of wheat and the colors of trees in Saskatchewan, although as far as I understand, Saskatchewan's not super tree covered. I haven't been to Saskatchewan. But just as an example, right? When we talk about, yeah, what indeed, right? Well, when we talk about uh, inductive reasoning, it's not necessarily a math term, right? Inductive reasoning is just sort of logic in general, or how you make conclusions about things in any discipline, right? Inductive reasoning is sort of inferring things based on information you already have. Deductive reasoning is sort of using rules that you know to be true in order to determine sort of how all future events will go, right? So we'll write that down here below here, deductive reasoning. Um, it's not the most elegantly phrased definition that there's ever been of deductive reasoning. Uses rules or algebra to prove how future trials will go. But that is exactly what it means, right? So you will see, Betty Ann, as you go through this unit, that some of the questions that you're asked to do are just kind of weird. Like, there's no math involved. It's just sort of asking you to like make assumptions about random flags and geography and symbols, or you know, but it's just showing that you understand basically that inductive reasoning is sort of using the info that you have already to make a best guess, pretty much. Deductive reasoning, though, is the real meat. Ask for a refund. Yeah, exactly, right? Exactly. Um, Deductive reasoning is proof, right? That's a term that you'll see in math a lot. Now, for whatever reason, when I went to high school, we barely covered proofs. Like, I don't think we did it at all, which put me at kind of a disadvantage when I went to university, and all of a sudden, like, profs were in like second and third year math courses were asking me to write proofs, and I was like, I've never done this before. So I had to learn the math and how to do a proof at the same time. It's not super complicated. All we're doing is using the sort of algebra to show why something is always going to work. So I would like to go through one of the examples that the book gives, right? And then so here, John had discovered a pattern when adding integers, it tells us, right? 1, 2, 3, 4, 5 makes 15. All these, he claims that whenever you add 5 consecutive integers, the sum is always 5 times the median of the numbers. So what we have here at the start is inductive reasoning, right? Because John saw these 3 patterns. And based on this pattern that he had, like I said, inductive reasoning uses patterns to infer conjectures about future trials. He made the conjecture based on these 3 patterns that any future time he did that, the result of adding them all together is going to be 5 times the middle number. Now, down below here, we want to prove that John's conjecture is true for all integers. Now, this part here, this is the deductive reasoning, right? So the deductive reasoning here sort of takes, we represent the situation in more general terms. Now, the figuring out how to represent the situation is the lion's share of the work in a unit like this. And there's no hard and fast rules. Unfortunately, you just kind of have to make sure each time you're doing this that what you're writing out is logically consistent, right? But for example here, x represents any integer, and s is going to be the sum of those, right? So here on page, what is this? Let me just, 26, right? What John said was then he was going to add together 5 consecutive numbers. So the sum of those numbers was going to be x minus 2 plus x minus 1 plus x plus 1 plus x plus 2. Now, why those? Well, we have to, like I said, it requires an understanding of algebra to be able to say that, all right, if x is any number, 5 numbers in a row, it's going to be 2 numbers. I can take 2 numbers before the x and 2 numbers after the x, right? If instead I did x plus 1, x plus 2, x plus 3, and x plus 4 over here, it would actually still work out fine. You're going to find that the answer is still going to work, just it's going to look a little different, right? But then once we take this and put it all together, then is where we end up with the 5x plus 0, or just 5x, right? So it's always 5 times this middle one. Say instead I was to do what I just said there, where instead of doing the 2 on either side so they cancel out, say I did x plus 1 plus x plus 2 plus x plus 3 plus x plus 4, which are still 5 sequential numbers, right? We'll see that the sum of those is going to be 5x plus, it's going to be 3, 6, 10, 5x plus 10, which is 5 outside of x plus 2, right? And we see, if I put brackets around all these guys so that it looks a little bit clearer, we can see here that x plus 2 is the middle of these, right? X plus 2 is right there in the middle. So we know now that the sum is still going to be 5 times the middle number. Just the middle number has changed. Instead of the middle number being plain old x, the middle number is x plus 2. But the deductive reasoning works out just fine either way. Right? But the book walks through this example fairly well. I do want to pop over here now. Let's see. I wanted page 31 next. Page 31. Okay. Yeah, these are some good examples here in the check your understanding on page 31. This is still math 2101A, and this is still unit 1. Page 31. Okay, let me zoom in a touch. So Chuck made the conjecture that the sum of any 7 consecutive integers is 7 times the median. Prove Chuck's conjecture. Well, that's just literally the conjecture that we did from John there in that previous example, isn't it? It's just there's 7 now instead of 5. But yeah, how about I just walk down through this one really quickly just to drive home the point, right? So the sum of 7 consecutive integers, it can be x plus right? And that's 5 consecutive integers. Start off with some number, and then, 1 more than it, 2 more, 3 more, and so on, right? So if I add these guys together, well, there's 7 x's. I already know that. 1 plus 2 is 3, plus another 3 is 6, plus 4 is 10, 15, 21, right? And then if I factor out a 7, I'll get s is equal to 7 outside of x plus 3, which is 7 times x plus 3. And we see that x plus 3 is indeed the middle of these numbers. So it's 7 times the middle number. So there we go. This is deductive reasoning. And we've proved it now. It's a proof. It's a proof that this conjecture is always true. We no longer need to go get other examples, right? Because if you wanted to prove this through inductive reasoning, what you would be doing is just sort of doing this a few different times with a few different sets of numbers. The thing about inductive reasoning is sometimes the conclusions it draws can be faulty, like we saw yesterday, right? On some, and we'll see it again here now in a second, because all you need to do to show that inductive reasoning is wrong is provide one single solitary counterexample, and then everything's out the window. Deductive reasoning, there's no way to prove to have a counterexample, at least not within this kind of math, right? Maybe in some proofs you could have like imaginary numbers with a counterexample, but sometimes we bracket that stuff off. Anyway, so number two here. Number two is another reason why I wanted to show these questions. Because number two is a bonkers question. Why in the world am I being asked this nonsense in a math course? Right? Like, Jim is a barber. Everyone whose hair is cut by Jim gets a good haircut. Austin's hair was cut by Jim. What can you deduce about Austin? Well, this looks like the kind of a question you would get in like some logic 101 philosophy course. This is not even computer science logic. This is like the very beginning of a philosophy logic, just like intro course or something. But what you're saying is, you can deduce that Austin's got a good haircut, right? Jim's a barber. We didn't need to know that, but we know that everyone whose hair is cut by Jim gets a good haircut. Austin's hair was cut by Jim. What can you deduce about Austin? You can deduce that he got a good haircut. What in the world? What kind of a question was that? That's all they're asking. We're not dealing with like formal logic symbols or if then and all this kind of stuff, which you could see later on if you went on and did more. But I'm not going to burden you with that here because, like I said, this is the only unit where we're getting into these kind of topics in this program. So I'm just going to spare you that. Just write down the conclusion that you would have, which for this question is you can deduce that Austin got a good haircut. That's it. Right? Leela drew a Leela. That's not how you spell Leela. Tarangalila. That's two E's. Come on, people. Leela drew a quadrilateral and its diagonals. What could Leela deduce about the angles formed at the intersection of the diagonals? Right? And we actually get a diagram for this if I scroll over a bit here. Well, what could she deduce? Looks here like she could deduce that these angles are the same and these angles are the same, right? We could deduce this one, this one, this one, add 180. We could deduce that these are right angles, but we don't really know that because it didn't say a regular quadrilateral. Yeah, there's a lot of things you could deduce. You could deduce that the angles are equal across here, right? Again, these are not super great questions because like I don't like it when a question sort of leaves the student wondering like, well, I could give this as the answer, but is that enough? Does this make sense as the answer? But for this unit, yes, yes, it does. It's fine. Just say something like, you know, angle, say the angle between J and M or whatever is the same as the angle between K and L, right? What I want to show is more the proof stuff, right? Because those are the questions that are a lot more straightforward to know, like if you're getting it right or wrong or anything like that. So question 4 here is a really good one. Prove that the sum of two even integers is always even. Well, I believe I showed this one previously as well, but I'm going to go ahead and show it again, right? The difficult part of this sort of math that we're doing is, like I said, knowing how to represent what they're talking about in terms, in algebra terms, right? So when it says prove that the sum of two even integers is always even, to do that, you have to know how to write an even integer in algebra terms. And 2x or 2y or 2z or 2 whatever, right? That's always an even integer because an even integer can always be divided by 2 evenly. Oh, we should also say um, we also need to get that in there as well, right? X is an integer, y is an integer, right? Because if x here was, like I said yesterday, if x was 0.5, all of a sudden then throws the monkey wrench in the whole thing. But if we prove, how can we prove that adding those two guys together gets us something even? Well, something even can always be evenly divided by 2. So 2x plus 2y is the same as 2 outside of x plus y, which can evenly be divided by 2. So I'll say since 2x plus y can be divided by 2, we know it must be even, right? So then say I went on to do number 5 here. Prove that the product of an even integer and an odd integer is always even. One reason I wanted to show this one too is to show you how we represent an odd integer. Well, like I said, we know we represent an even integer as 2x, but how could we do an odd integer, right? Well, an odd integer is going to be, say, 2y plus 1. And the reason we do that is this sort of, that's kind of our reasoning, right? And again, this is where the real meat of this unit comes in, is remembering how we're going to write out concepts like an odd integer in algebra, right? So I did 2y plus 1 because we know that 2y, same as up here, we know that 2y is even. So if we take an even number and add 1 to it, we know we now have an odd number, right? Or subtract 1. You could do that too. That's fine, right? But we know that 1 bigger or 1 smaller than an odd integer in an even integer is what an odd integer is, right? So here now we know this is an even integer. Well, that's an odd integer. We multiply these two guys together. We're going to get 4xy plus 2x, which we can also call 2 outside of 2xy plus x, right? So I could say then that, um, see, I'll do this in a different color so we can see that I'm actually, right? Since 2 outside of 2x plus x can be divided by 2, it must be an even number, right? Because of this 2 on the outside, right? So that's basically how we would go through and prove these things, right? It is, unfortunately, it's very difficult for me to provide you, say, with like a list of all the possible sort of algebra ways you would have to represent these concepts, but there's not all that many that are covered in this course. And if you're confused about one, just let me know. I'll definitely be able to help you with some things on a test, like um, or especially on an assignment or anything like that, right? So if you're confused about how to represent something, please just let me know, and I'll see what I can do about that. One more page that I want to go over from your textbook to show this topic in better detail is this mid-chapter review here. This pages 34 and 35. I think these are really good ones to give you sort of a good overview of what this topic is about. 2101A, Unit 1 still, page 34. Okay, so let me zoom in a little. Frequently asked questions. I like FAQ. I'm an old school internetizen, right? I like FAQs like down below. You gotta have a FAQ right on the start of your website, whatever the website is. It's always the most important part. Um, what is the difference between inductive and deductive reasoning? This is a well phrased answer here, actually. Inductive reasoning involves identifying patterns through examples to develop a conjecture or a general statement. A set of examples, however, is not a proof, right? There's a great phrase that the plural of anecdote is not data. That's a bit of a it's a bit of a statistician joke there. But what it means is like just because you have anecdotes of something that you've heard from your friends or other people or whatever, that doesn't necessarily mean that that is just how those situations play out for everybody all the time. And that's the exact same thing that we're talking about here, really, right? Is that just because you have some examples of a pattern, that doesn't necessarily prove that it's always going to pan out that way, right? These examples can only support the conjecture, like I said, right? In comparison, deductive reasoning proves a rule which can then be applied to any specific case. Deductive reasoning is a lot more sort of mathy, I guess, for lack of a better word. But deductive reasoning is more what you're going to be spending some time on here, more so than inductive. Although it is important to know inductive. Um, Inductive is more like what you would see in stats, I guess, whereas deductive is more like pure math. Where in pure math, you're sort of concerned more with the fundamental rules of mathematics that mathematicians are discovering as we work through new mathematical concepts and whatever. Whereas inductive reasoning is kind of like statistics, where you're seeing these results and then you're saying, well, what sort of conclusions can we draw based on these results? And are these conclusions valid? How often are they valid? And is it even really appropriate to make these conclusions? Sort of the eternal questions of statistics, right? So inductive reasoning here, we see a pretty good example, like I said. 1 plus 2 is 3, 4 plus 5 is 9, -6, -7, -6 is -13. From the pattern shown in the examples, I think the sum of two consecutive integers is always an odd number. Okay? Why is the sum of two consecutive integers always an odd number? Well, we know that that's got to be the case, right? Of course it's true. Because we see here, like x plus 1, those are two consecutive numbers. We add those together, we get 2x plus 1. Right? 2x plus 1 is just the way that we represent odd numbers in general, right? It's 2x, which is always even, plus 1 makes it odd. And now we get down to the other topic that I wanted to briefly talk about in this unit, is what's the purpose of finding counterexamples? Well, why do we do that? Well, it says counterexamples are examples that disprove a conjecture. So counterexamples may be used to revise the conjecture. And this is a really well-phrased page, I think. For example, conjecture, in November, the daily temperatures in Hay River, Northwest Territories do not exceed 10 degrees Celsius. Counterexample, November 19th, 2005, the maximum daily temperature was 11.8 degrees Celsius. So a revised conjecture is that in November, daily temperatures in Hay River do not exceed 10 C more than once every 5 years, right? So that's sort of a caveat that they included there to make allowance for the counterexample. Excuse me, my nose is really itchy today. It's these allergies, boy. It's these trees around me, you see? See, I'm getting lots of pollen from these trees that are next to me. Trees are actually a big source of pollen, you know? I thought it was all grass, but turns out no. Turns out evergreen trees are just barfing that stuff out. Anyway, so I would like to show, let's see. Yeah, let's go through this lesson 1.1 here. A medicine wheel consists of a cairn of stones surrounded by a circle of rocks with lines of rocks setting from the center of the circle. The Moose Mountain Medicine Wheel is a sacred site created by First Nations peoples more than 2,000 years ago. Its exact purpose is not known. Make a conjecture about the purpose or usage of the medicine wheel. Now here, this again is an example of kind of a gimme question, right? This question is free marks because there's no way to prove your conjecture is wrong. I could say that maybe it's a sundial. That would be my guess. Maybe it's something to do with determining the season, like what day of the year it is, by the path that the shadow takes over the course of a day, right? I could say, yeah, so my conjecture could be because, so there we go. That's a conjecture, right? Because there's rocks arranged in a circle around a higher rock in the center, maybe the medicine wheel is a type of sundial. Hey, that's a conjecture that you can make, totally valid based on that picture. It's not one that we can prove right or wrong. At least maybe anthropologists can. I mean, even that would be difficult, right? Because how do you like? I guess anthropologists must have a pretty hard time sometimes with like or cultures with oral tradition. Like oral tradition is obviously very important in a lot of First Nations cultures, right? But that must make it more difficult for the anthropologists who are trying to study and record this because the nature of oral storytelling and oral history is that it can change from one generation to the next. But how can we prove or disprove these conjectures? Well, like I'm saying, that's really difficult in these cases. But for our purposes, this is totally valid. It's a conjecture that I've drawn based on the information that I'm given, and that's all that it's asking you to do. Even though this is a math course, not a folklore or anthropology or ethnography or anything like that. What's another good one here? Yeah, okay. Yeah, number eight. Number eight's a nice one. Let's go down through number eight here. And that maybe should be a good example because sometimes you'll see little games like this, right? Little games on Facebook or whatever that say like take your age and then add 72 and then divide by 12 and then times by 12 and then subtract 72 and oh my god, it's your age again. How'd that happen, right? you know that's sort of the kind of thing that we're talking about here. So use inductive reasoning to make a conjecture about each number trick below. Okay, so I'm going to tell you right now, there it's pretty likely to have a question like this on your test, right? So file that one away in the old gray matter. But to get full marks on a question like this on a test, I would want you first to show what inductive reasoning is in a situation like this, and then show what deductive reasoning is in this kind of a situation. So inductive reasoning is showing a pattern through, we'll say, through multiple trials. Showing a pattern through multiple trials, right? So I would want you to just do maybe 2 or 3 runs of this sort of number game and see what answer you get. So choose a number. So I'm going to choose 3. Add 3. Did it. Multiply by 2. Okay. Add 4. Got them. Divide by 2. Subtract the number you started with. Well, that's a bit of a cheat, isn't it? Okay, what is the result? 5, right? So, but now we've only done it once, right? So we don't have enough. This is not enough to call this deductive reasoning yet, so let's pick some more numbers. I'm going to pick 11. Oh my God, came out to be 5 again. All right, just for a good show, just for a good show. Let's keep on going. Right? It just says choose a number, so let's do negative Negative 6.5. Let's go ham on this one. Let's make this hard. Negative 6.5. Negative 6.5 plus 3 is going to be negative 3.5. Negative 3.5 times 2 is going to be negative 7. Right? What was the next step? Add 4. Negative 7 plus 4 is going to be a negative 3. Negative 3 divided by 2 is going to be a negative 1.5. Negative 1.5 subtract negative 6.5 is going to be a 5. Oh my god. Oh my god. All right. It's magic. It's like magic. I'll tell you what it is. I'll tell you what it is. It's this last step where we're subtracting the same number that we put in. Right? But anyway. So then if I go on into deductive reasoning, using algebra to prove a universal case, well, like I said, this is the exact kind of question that you're going to see on a test or something like that, right? So then my first number instead is going to be x, right? Then I'm going to have x plus 3 for my next step because I'm adding 3. Then I'm multiplying by 2, so I'm going to have 2 outside of x plus 3, right? Then my next step I'm adding 4, so I'm going to have 2 outside of x plus 3 plus 4, excuse me, right? Or I could call this, holy moly, my camera got dark all of a sudden. What is going on here? Hold on just 1 second. Or 10. 15 maybe. Like an unspecified short amount of time. Kind of what we mean by 1 second. All right. So, how about instead, and I multiply these out, I'll call this 2x plus 6, right? Then I'm going to add 4. The next step I'm going to add 4, and I'm going to call this, I'm going to move this up here. I'm going to call it 2x plus 10, now that I've added 4. Now I'm going to divide each thing by 2, and I'm going to call this x plus 5. Now I'm going to subtract an x. It's going to be x plus 5 minus x, which is just 5. Right? So my deductive reasoning showed as I went through each step, I ended up back with the 5 every time. Okay? So let's see. Yeah, let's do one more. Let's do one more here as an example of to show what we have to do here. Yeah, so number 11 here, about as tricky as it's getting for these algebra-based ones. But we're proving that the difference between the square of any odd integer and the integer itself is always an even integer. Boy, there's a few twists and turns to that one, isn't there? So first up, we're going to need to represent an odd integer. When we know that an odd integer, I can call it 2x plus 1, right? As we went over, we can't just call it x. It has to be 2x plus 1, right? Because 2x is always even, which makes 2x plus 1 always odd. So now the difference between the square of any odd integer, so the square of an odd integer is going to be 2x plus 1 squared, which is going to equal 2x plus 1. I'm just going to write it out. Multiplied by 2x plus 1. So now we're going to head and do our FOIL, right? So we're going to call this 4x squared plus 2x plus 2x plus 1, or 4x squared plus 4x plus 1 is the square of any odd integer. I know it's looks like a lot of writing for something that sounds so simple, right? But this is how you do it. The difference between the square of any odd integer and the integer itself. So the difference means subtract. So we're going to have 4x x squared plus 4x plus 1 subtract 2x plus 1, right? So that's then going to equal 4x squared plus 2x, right? And we can call that, just move up a little bit so you can see on the screen there, we can call that 2 outside of 2x squared plus x, right? There we go, right? Since 2 outside of 2x squared plus x can be divided by 2, it is an even number. So that's kind of, yeah, that's really all that it's asking to do there. I mean, I know to say like that's really all. Sounds like I'm downplaying it a little bit. Um, I recognize that this unit is a fair bit different than the math that you have seen so far, and indeed a fair bit different than the math that you're going to see afterwards as well. Again, right, you're not going to be asked to do very many proofs over the course of your program. It is important to know sort of the difference between inductive and deductive reasoning. But again, since this program doesn't really go very deep into stats or anything like that, we're not really going to be belaboring that point very much, right? But to get through this unit, it is still important to know those ones. Basic lesson, like I said, is that like this page here says, right? The difference between inductive and deductive reasoning. Inductive reasoning involves identifying patterns through examples to develop a conjecture, whereas deductive reasoning proves a general rule, which can be applied to any case. Right? That's a really succinct way of phrasing it. And the other lesson to learn here is that yes, the questions sometimes are really silly and really conceptual, like this medicine wheel one. I mean, it's silly in the sense that it seems silly as a math question to have this, but that's what it is, right? It's no more complicated than that. Don't overthink it. is is one important lesson for this unit. Okay, so I think that's a reasonable look at all the stuff here. Let me just move myself down a little bit to get on my own way, metaphorically and literally. Um, yeah, I hope that was useful for you, Betty Ann, and Renetta, who probably stopped watching after I went through her questions, but it's what you do, obviously, right? She's not gonna need to get onto this in a while. Oh, you're very welcome. Yeah. If you have any other questions about this unit or anything like that, please let me know, and I'll send you the link to the video afterwards in case you want to take a look over it again or whatever. Right? Yeah. Just let me know if there's any other questions. I hope that you're finding the stream useful. And yeah, enjoy your day. Stay safe, and I hope to see you again tomorrow. Right? Thanks for stopping by. I'll see you later.